Sparse Categorical Cross Entropy. In the last lecture, we learned about categorical cross entropy loss. This time, we are going to learn about a very similar loss function, conceptually the same loss function, but this time it is sparse categorical cross entropy loss. The difference is, in the last case, when we learned about categorical cross entropy, the standard one, we had learned that it requires the true labels to be in one hot form. This is what we had learned. What is one hot form? Okay, let us first go to the terminology, then we'll understand what is one hot form. We had introduced K, which is the total number of classes. In the last lecture also we had discussed this. K that we use will be total number of classes. Then there is something called Y cap. X is your input. Let us say X is your input. X is the input. Then there is something called Y cap, which will be your output. That is the raw logit output. Okay. Whatever output your model is providing, that you will call as Y cap. Then there will be something which is the actual label corresponding to each input X, which is in your training data. You will have an actual label called Y. And this Y we had told is a one hot vector. What is meant by actual label? Each of the input example X, let us say X is your input, that will belong to one among these K classes. We told that total number of classes is K, which means there will be class 1, class 2, class 3 up to class K. Among these, each input will be actually belonging to one particular class. Let us say class 3. That is your real class or the true label. This true label is what you are calling as Y. But the speciality that we discussed with Y in the last lecture on categorical cross entropy was that this is always represented as a one hot vector. What is a one hot vector? It will look like something like this. Let us say 0, 1, 0, 0. This vector denotes that this particular input X belongs to class 2 because this is corresponding to class 1, this is class 2, class 3, class 4. Among these entries in this vector, one will be having the value 1 and all others will be having the value 0. Whichever is having value 1, that is the true label. So this is how true label will be denoted whenever we are dealing with categorical cross entropy as the loss function. But what happens is, in reality when you do, sometimes you may have label in this form, but sometimes you may have to deal with labels which are integers. So instead of this, let us say I am saying my Y value is 2, which says it belongs to class 2, or maybe I'll say class 3, which means it will belong to class 3. In this case, instead of one hot vector, if I am having just the true label as an integer, then instead of categorical cross entropy, instead of this, you will be using sparse categorical cross entropy loss. So when you are dealing with machine learning, let us say you are using some inbuilt loss function, then you will generally see examples, options of categorical cross entropy as well as sparse categorical cross entropy. Now you should understand in which cases should you use categorical cross entropy and in which cases should you use sparse categorical cross entropy. That is why the main factor that determines it is if you are having a multi-class classification problem in which you are having K classes, then if your true label is in the form of one hot vector, then you can go for categorical cross entropy, and if it is in form of an integer, then you will go for sparse categorical cross entropy. Okay. So let us understand how this loss function works. What exactly is this loss function? So this time it is not one hot vector, it will be integers. So it will be something like Y true is equal to 1, which means it belongs to class 1, something like this. Okay. So this is your true label, which is integer. So this time you are having integer to denote your true label. Let us understand the next step. In the last lecture, we discussed that whatever you are getting as output, this is raw logit. Logit means it is a real number. It is not a probability. Instead, it is a real number. Corresponding to each class, you will have a real number, which is a value corresponding to the output provided by model. So your model is something like this. You give X to the model. What did the model produce? It produced y cap, which is the raw logit produced by the model. The next step is, from this logit, you have to generate probability. How did we generate probability in the last lecture? We said pk cap, that is corresponding to each class, you have to find probability. Corresponding to each of the output y cap, that is y cap is also a vector. It will have y1 cap, y2 cap, up to yk cap. So corresponding to each class k, there will be a real number. This is called as logit. This real number has to be converted to corresponding probability. That is what we are doing. So this pk cap, this will be equal to, this is the softmax what we are going to take. It will be softmax of your yk cap, whichever is the yk cap. This will give you e power yk, this I'll remove from here, e power yk divided by sum over all the e power yks. Let us say j equal to 1 to k through all the e power yks. What will you do? E power yj. So here you are taking j, that is why I took j. E power yk divided by sigma j equal to 1 to k e power yj. This is your softmax function. What will this do? We already discussed 2 times in the last binary cross entropy lecture and also the the categorical cross entropy lecture. We discussed about these things, how probability works here. So one thing you have to understand is, this is interpreted as probability because the value of this will always be between 0 and 1. And if you sum all the probabilities, all the pk's, if you sum, you will get 1. That is why it is a probability distribution. Okay. So the next thing you want to understand here is, for finding sparse categorical cross entropy, till this point we reached till finding probability. Next thing is finding the loss. In order to find the loss, what did we discuss? We discussed that first thing you should find out likelihood. So what is the likelihood here? Likelihood of theta, this can be written as p cap. So let us say corresponding to this particular entry, we'll say py cap. Okay. Then this likelihood, this has to be converted to log likelihood. Why are we doing this? Because log is always numerically more stable. It is easier to deal with. So you will take log likelihood. So I'm directly doing this because I'm expecting that you've already been through the previous lectures. So these parts, we follow the same path in all those lectures. It will become log likelihood. And then whenever here you have to maximize the likelihood of this. Instead of maximizing likelihood or instead of maximizing log likelihood, both are the same. Instead of this, what are we going to do? We are going to minimize negative log likelihood. So here what you have is log likelihood. Your negative log likelihood, this can be written as minus log py cap. So this negative log likelihood is actually your loss function. Another way of understanding this is, let us say I'm writing this here. This is my loss function. So this this was likelihood. What I'm writing here is loss function. Loss function is negative of log likelihood, NLL. Okay. This can be written as minus log py cap. Okay. So when I write py, it is y true. Okay. That should be understood here. When I say py, it is the true label. Okay. Among y, whichever is the y true, the true label for this particular example, that is what I'm pointing out here. If you compare this with categorical cross entropy that we learned in last lecture, then you will be very clear of what is the difference and how did we come to sparse categorical cross entropy from categorical cross entropy. Okay. So let us just see what is the formula in case of categorical cross entropy, and then let us see how we formed it in case of sparse categorical cross entropy. Okay, so what I'll do is I'll first write case of categorical cross entropy. So in case of categorical cross entropy, we did something like this: minus sigma. What did we have to sum? We had to sum over all the classes. So it will be sigma k is equal to 1 to k. Let us say over all these classes, we summed yk into log pk cap. So this was the case. Here, if you remember, what we did in categorical cross entropy is this pk cap was the probability for kth class and yk was the true label for the kth class. If you see this true label y, it was composed of a one-hot vector, something like this, which means among all the terms in this summation, all the terms will be 0 except one particular term, which is the true class. If you see this, when you do this summation, what happens is yk's value will be 0 in all cases except one particular case which corresponds to the true class. So in the summation part, only term that remains will be that particular term which is having k, which is the true label. If it is true label, yk will be 1 and your log pk cap is the only term which will remain. So the summation won't remain because all other terms will be 0. So in categorical cross entropy, effectively your loss function is this only. Now you can see the similarity with sparse categorical cross entropy. In case of sparse categorical cross entropy, it is exactly the same. If you see, the loss function is exactly the same. The only difference is instead of denoting it as a sum over all and then saying because it is one hot vector, all are zeros and only one remains. Here what we do is we are only taking the probability corresponding to the true class. We are just ignoring all the remaining classes. So in case of sparse categorical cross entropy, because you are having integer classes like 1, 2, 3 and so on, instead of one hot, which would mean instead of 1 you were writing 1 0 0 0, then instead of 2 you were writing 0 1 0 0, something like this. So instead of this time you are having direct integers, because of which what are you doing? Corresponding to that particular integer, the true label, whatever is the probability, only that is what you are going to consider, and then your loss function will be minus log pk cap or py cap. Py cap is the true label. This is very simple to understand, and if you could relate all the lectures, that is initial lecture that we had on binary cross entropy, then what we had on categorical cross entropy, and then now on sparse categorical cross entropy, if you relate all these lectures, you will understand that everything is the same concept. It is just that when your labels changed, the true labels changed, or the number of classes changed, we just adjusted the formula accordingly. All these are following the same logic. So once you understand this, getting a grasp on this becomes much easier. Mathematically, you will be clear. Okay. So this is the loss function. What is the other thing we want to find? Okay, one more thing. Here we considered only one particular example. Instead of this, in reality, you may have n examples. In your data set, you will have n samples. Then how are you going to find the loss? Then your loss will look something like this. You have to take the average over all those. So minus 1 by n. Then you have to sum over all the n different samples. So I is equal to 1 to n. If you take sum and you divide by n, then you will get the average loss. Okay. So 1 by n, sigma I is equal to 1 to n. Then for each sample, you have to apply the above formula. How will you apply? Log. Instead of py cap, you can write something like this. Pi cap and pii yi cap. So what I meant when I wrote pii yi, this is that this is the probability of true label corresponding to the ith example or the ith sample. That is what I meant here. So by yi, I meant true label for the ith class or ith sample. Okay, you have samples 1, 2, 3, 4 up to n. For each of these samples, there will be a correct class. Whichever is that correct class, corresponding to that correct class, you want to find out the probability. So that is what I am denoting as PIYI cap. Okay. So this is the loss function you will have in case you are using sparse categorical cross entropy and you are having n samples. And one more thing, in the previous lectures we discussed about the maximum likelihood estimate. That exactly is what we used here. That is, we discussed something like this. You want probability of, let us say, y true given x and theta. Something like this is what we discussed. This exactly is the negative log likelihood that we minimized. So from here only we started. This is where we started here. Okay. So it is the same concept that we discussed in the last lectures. So this is it about sparse categorical cross entropy.